All right, go ahead and get started for today. We are in section 5.3. We're kind of continuing that. So we have another graph we're going to go over. We were talking about these yesterday, transformations. And so for this kind of graph, we did a similar one yesterday with that, where we're going to change this into instead of a fraction, we're going to change it to a base of a regular whole number. So we're going to do that by changing the 1/2. There's a 2 to the first power. So if we bring that up to the top, like we did yesterday, then we get this. And then we can also, when we raise a power to another power, you're going to multiply the exponents. That was one of the rules we talked about yesterday. So that's going to be a -2 to the -x. And that's what we're going to have right here. So we changed the 1/2 base into a whole number base there, but now we have two negatives. So let's first take a look at the 2 to the x graph. That's this one. We talked about that yesterday. We have the point 2, 1, and then we have 0, 1 right here. Now we have two different negatives that's here. What that's going to do, it's going to be two flips. So I'm just going to draw a little sketch first for each one. So if I have this graph right here would be y equals -2 to the x. So the negative out front would flip it over and it would look like that. Well, then I need to apply a negative in the exponent. So what that's going to do, it's going to take this graph of y equals -2 to the x, and it's going to flip that one over the x-axis here. So this is going to be y equals -2 to the -x. So the graph is actually going to flip and go down like that. Well, then we have to raise this up by 3. So the 3, first of all, that's going to be our horizontal asymptote. So we can draw that in first. The number on the end is always that one. And the graph needs to look like this shape. So it was flipped over. So this point that was at 0, 1, that's going to flip over and actually be down here. And this point kind of gets reflected over to kind of a cross. We reflected over the x-axis and over the y-axis. And so this dotted line is going to be the y equals -2 to -x graph. So now I have my exact points that I'm going to use. So now I just need to take this dotted line graph and raise it up by 3. So this point's going to move up 1, 2, 3. So it's going to be at 0, 2. This other one, if I move it up 3, it's going to be at -1, 1. And then I can just draw the graph in like this. Okay, so that's going to be what the overall graph is going to look like. So we had, again, this graph ended up having two flips because there's a negative in the exponent position. So it ended up being a negative out front and a negative in the exponent position. So now we just need to answer these other questions along with that. We have domain and range. So domain, again, for all these are going to be -infinity to +infinity. We have range. Range is going to be the y values the graph uses. This is going all the way down to -infinity, and that's going to go all the way up to the dotted line, which is 3. So -infinity to 3. So range. Horizontal asymptote, we just said is actually this dotted line. So that's just going to simply be y equals 3. Okay. And then that's all they're going to ask for this. There's no vertical asymptote on these. There's only a horizontal asymptote we have. Okay. All right, so the next kind of problems that we're going to transition to is something that's called the equal basis property. Now, some books have it as the equivalence property of exponential expressions, but that's too much to say. It's too long. So I'm just going to call it equal basis property. And basically, here's what the property says. It says if a is raised to the u and a is raised to the v, so both the bases are the same, then the exponents have to be equal to each other. So in other words, if I have 2 to the x equals 2 to the 7th power, then x equals 7. That's basically how that property works. So just for an example here. So we can use that to solve for the missing variables if they're in the exponent position. So if the bases are the same, that means the exponents have to be equal as well. So that's an example of using the equal basis property. So let's apply that now to some these equations down here. Now each of these, you want to try and get these to be the same base. Okay, so we have a 4 that's here, and we have a 64. Now both of these, 4 and 64, they can be written as bases of 2 and bases of 4. So instead of doing extra work on this, we'll just see if 64 can be written as a power of 4, and yes, it can. So we have 4 to the x minus 2, and then 64 can be written as 4 times 4 times 4, or 4 cubed. So then since the bases are equal, we're going to set the exponents equal. X minus 2 equals 3. Add 2 to both sides, and we get a 5. So 5 is going to be your answer. That's using the equal basis property. This next one, the one that we just graphed, we changed the 1/2 into a power of 2. So I'm going to do the same thing on this one. This is the same thing as 2 to the negative 1, all that being raised to the 1 minus x. And the 4, I'm also going to write that as a base of 2. So now I have both the bases are the same. When I raise a power to another power, I need to multiply the exponents. So I have negative 1 times 1. So I have negative 1. Negative 1 times negative x is plus x. So now I have the bases are equal, and I'll just set the exponents equal to each other. So I'm going to get negative 1 plus x equals 2. If I add 1 to both sides, I get x is equal to 3. X equals 3 would be the answer. Okay, so this one here, 27 and 9, both of these can be written as powers of 3. So what I'm going to do is change each of these, the bases, into powers of 3. So for the first one, I have this here. So 27, I changed to 3 to the 3rd, and that's being raised to the x plus 2 on the other side. I can write this as 3 squared. So now I have both of these written as powers of 3. When you raise the power to another power, you multiply the exponents. So that's what we're going to do here. We have 3x plus 6. And then this is 3 to the 4x, because you're multiplying those together. Now you have the bases are equal. So the equal basis property says once the bases are equal, you can set the exponents equal. 3x plus 6 equals 4x. Just subtract 3x from both sides, and we're going to automatically get our answer of 6. Okay, so x is equal to 6, and that would make that equation true. This next one, we already have 3's in there. So we have a 3 on both sides, but we have a square root on that side. What we can do on that is we can change the square root into a 1/2 power. So anytime you have a square roots can always be changed to a 1/2 power. So I have 4y minus 1, and then I have 1/2. Now I'm just going to set those exponents. 4y minus 1 equals 1/2. Since the bases are equal, we can set the exponents equal to each other. One way, if you don't want to deal with the fractions, you can just multiply the whole equation by 2. So that's what I'm going to do here. I'm just going to take both of these and multiply it by 2. And that's okay as long as you do the same operation to both sides. 8y minus 2 is going to equal 1. So then if I add 2 to both sides, I'll get 8y equals 3, and then I can divide both sides by 8 to get 3/8 as the answer. So these are not always going to have whole number answers. Sometimes they'll have fractional answers like that. So again, I multiply both sides by the 2 is the denominator. So I just multiply by that to clear out the fraction. So that way it's easier to solve for. The next example that we have has an E, and then but on the other side we don't have an E. So it may look like this is a problem that we can't solve by using the equal basis property because we don't have the same base on both sides. But we are able to make these both the same base because there's a 1 here. Now what we know about the 1 is that you can have anything raised to the power of 0 is 1. So what I'm going to do is be a little bit creative here on how I rewrite the 1. I'm going to change that into e to the 0 power. We know that anything raised to the power of 0 is 1. We talked about that yesterday. So I'm going to change the 1 into e to the 0. So now that both the bases are equal, I'm going to set the exponents equal like that. And then I'm going to subtract 5 from both sides, divide by 3, and I get negative 5/3 would be the answer. Now, a question often comes up is, well, what if that wasn't a 1? What if it was like a 2? Well, then that is actually something that you can't use the equal basis property, and that'll be something we'll learn in the next section that involves logarithms. But up to this point right now, we can change it into, because it's a 1, we can make it e to the 0. That's the only thing it works for. If it was a 2, a 3, or something else, we couldn't change it into e to the 1 or e to the 2, something like that. We couldn't do. But for this particular example, we can. So we're able to change the 1 into e to the 0 and solve for it. Now, sometimes you may have more than one answer on these. So here's an example of one where we're going to get more than one answer. First of all, what I notice is I'm raising a power to another power. So I want to multiply the exponents here. So I'm going to multiply the x times both of those. So I'm going to get x squared minus 2x. So I'll just multiply each of those. On the right-hand side, I'm going to change that to the same base. So an 8 can be written as 2 times 2 times 2, or 2 to the 3rd power. So now I have equal bases, and I can set the exponents now equal to each other. X squared minus 2x equals 3. These kind of problems, if you have a quadratic that comes up, you want to set them equal to 0. So we're going to subtract 3 from both sides to get a 0 here. Now that I have it set equal to 0, we can use whatever method you want to use to solve for it. Factoring is going to be the easiest. It'll be faster than quadratic, so it's probably a better choice on this example. 3, there's only 1 and 3 of the powers on that. You're looking for two numbers that the signs where they add up to -2. So you want to do a -2 and a positive 1, because that way -3 plus 1 will give you a -2. Now you're just going to set both of these equal to 0. X plus 1 equals 0. X minus 3 equals 0. And you get x equals -1, and you're going to get x is equal to 3. Those are your two answers, -1 and 3. Now there is one more problem that I added to the guided notes that you may not have on your original one. I am going to go ahead and update the guided notes section, the written notes section in my open math with this new problem. But this is similar to one that is in the homework, so I want to show how to do one of these, because I often get a lot of questions on this, so I thought I'd just go ahead and throw it into the notes, and so that way we know ahead of time how to do it. It says determine the exponential function whose graph is given. So we see right here that the graph goes through the point 1, 7. Okay, so it goes through 1, 1, 7. These graphs of this type, we see that it is increasing and going up like that. We talked about these graphs a little bit yesterday, but these all are going to be the form of some number raised to the power of x. We've already looked at the 2 to the x graph, the 3 to the x graph. We already had that. And the way that these work, let me go back to the one that I did earlier, the one that we started the class with here. So here, this was the graph of 2 to the x, And as you see right here, it goes to the point 2, 1. So the way these kind of work is anything that you put in here is a 1. Whatever the base is, it's going to give you that value. This is so this is actually, I made a mistake on this one. It should have been 1, 2 actually. Okay, so 1, 2 was the coordinates on that. But if you put a 1 in there, you get a 2 for the y value. So 1 and 2. So whatever this base is, if it's a 5, it would just be a 1, 5, or whatever base it happens to be. So all you have to do in order to get the equation is just look at what the y value is there when x is equal to 1, and the y value is going to tell you what the base is. So if I go back to this one over here, the one that we're working on, because I have, if I put a 1 in there, I get a 7. That means 7 is going to have to be the base, which means that the equation for this is just going to be 7 to the x. That's all you have to do to solve for it. So it's actually a little bit easier than you would think to do. Just look at whatever graph they give you. Just look at the at the x value of 1. You just look at the y value, and that y value will tell you what the base has to be. And there's no flips or shifts of any kind here, so it's just going to be raised to the power of x. Okay, if you put a 0 in here, you would get a 1, and it looks like that's where it goes through on the graph as well. So this would be the correct equation for that. So I just wanted to go through that last example for you because I get a lot of questions on this typically for homework. So now we can cover that ahead of time. All right, so this is everything from 5.3 is now complete. So now we're going to move on to the next section, 5.4 on logarithms. Okay, so what we're going to talk about here is, first of all, what a log actually is. So a log is actually a type of inverse. So if we take a look at, we're going to start with this right here, y equals b to the x. Let's suppose we want to find the inverse of this. So inverses, we talked about the way you do that is you switch the x and the y, and you'll get this. You'll get x equals b to the y. But then if we wanted to solve for y, we really don't have a way to do that. And so this is why we need to know a log. So this right here, this is called the exponential form. Now this is still going to be the inverse of y equals b to the x. So we have x equals b to the y. So the way that you actually solve for y is we're using something that is called a log. It's a log. It's a thing that's on your calculator, and we have a log base b of x. These two things, the exponential form and logarithmic form, are actually saying exactly the same thing. They're both the same equation. The only difference is one solved for x and one is solved for y. So the log is a operation that is used to allow you to solve for exponents. That's typically really what a log is. Okay, so a log is a type of exponent that allows you to solve for that. Now the little base that's here, that can be any kind of number. Okay, but one thing to point out is that your calculator only has 2 types of bases on it, and we'll talk about that a little bit later when we get into there's a couple calculator questions, and so we'll talk about what those mean later. But there's 2 different bases your calculator can do, but just know that that can be any whole number. It's got to be greater than 1, so 2, 3, 4, 5, anything like that. So that's what that is. The first couple questions that are in here are ones where you're just going to change between the 2 forms. So you're not going to solve these. All they want you to do is to solve or write it into the correct equation. But again, you don't have to actually solve for anything. So we want to change this into exponential form. Well, if we look at the log form and the exponential, the way it works is you have if you're starting with the log form, you look at the base b. So base b is being raised to the number after the equal sign. It equals whatever is left over inside the log. So I'm going to do the same thing here. I'm going to take the base m. I'm going to raise it to the number after the equal sign. And it's going to equal whatever I have left over in the log. So that's all you have to do. Again, you don't have to solve for this. You just have to leave it like that as an equation. Next, this one here, we're going to take the base, raised to the number after the equal sign. So c to the 8 is going to equal 6. The base raised to the number after the equal sign equals whatever you have left over. And that's, again, all you have to do there for that one. Okay, now I'm going to leave this up here at the top so we can do this one. We want to change q equals 1.4 to the fifth power into log form. If you're going from exponential to log, then what happens is the base of the exponent becomes the base of your log. The y goes after the equal sign, and then the x goes inside the log. So if I want to do this one down below here, what I'm going to do is I'm going to first start by putting in a log base of 1.4. I'm going to do that first. Okay, and then the 5 is going to go after the equal sign, and I put a q left over right there. So I have, that's how we do it. 1.4 becomes the base. The exponent goes after the equal sign. And I could have put the equal sign on the other side as well. It doesn't matter, actually. And then whatever's left over, q, that's the one that goes inside the log. So let's do another one of those. Now that we know kind of the pattern. So again, the base of the exponent becomes the base of the log. The exponent is going to go after an equal sign. The 8 is whatever's left over that goes inside the log. Okay, yeah, we don't have to compute this. We just have to turn it into log form, and then we just leave it like that. That's it. Let's do one more of those. We want to change it from the exponential form to log form. So first we've got log, and that's going to be a base of e, because e is the base there. The y goes after the equal sign, and then I have an x. Now, if I have a log that is a base of e, that's actually a special kind of log. That's the same thing as y equals ln x. So these two are exactly the same. This is called a natural log. Okay, so ln x is called a natural log because of the n. That's why there's an n there. Okay, so log base e is the same exact thing as ln x. This is a type of log that your calculator will do. If you take a look at your calculator, if you have one, there's two different buttons that you'll see on there. One is an ln button, and the other is a log button. By the way, if you see, so this is separate from this problem I just did. If you see log with nothing after it, like that, this is exactly the same as y equals log base 10 of x. So typically when we have a log base 10, since these are more common, they're usually just written without a number underneath. So if you see a log with no base underneath, automatically it's a base 10. These are the two bases that your calculator will do. These are the only two bases your calculator will do. It'll do a log base e, and it's going to do a log base 10. And those are the two buttons that are on your calculator. So for instance, when I see these problems right here, we're going to do in the calculator. So first of all, I've got a log base 5. Because there's no number underneath, there's no base there, that's a log base 10 of 5 is what you're doing. This is one that your calculator can do. Okay, so we just want to put that into the calculator and round it to the nearest thousandth. So we want 3 decimal places. Okay, so when you put that in there, okay, make sure you use the correct button. So you want to use the LOG button there. Okay, so if you try putting this in your calculator and you get an error, that means you might have one of those calculators where you have to put the number in first and then hit the log button. So that's if you have a TI-30XA calculator, you'd have to put the 5 in there and then hit the log button to get the answer. But most graphing calculators, you should be able to just type it in exactly as is, and it's going to give you the answer. You have to round it to the nearest 1,000, so 3 decimal places. So it's going to be 0.699. That's rounded to 3 decimal places. Okay. Next, I want to do ln7. So again, depending on the calculator you have, you might have to put the 7 in there first and then hit the ln button afterwards. This is nearest 100. So this here is 3 places. This is 2 decimal places. So thousandth is 3 decimal places, hundredth is 2 decimal places. So 2 decimal places, you should get 1.95 as the answer on that. Okay, so that's just doing that in the calculator. This equal basis property that we just talked about in the last section is one that we can also use here. So as I mentioned, your calculator only does these two. It does log base 10 and log base e. But the question comes up, well, what if it asks me to do a log of something else like this? Log base 4 or 64. Now, this is something that most calculators are not able to do. I suppose if you have one of those fancy calculators like a TI Inspire, something like that, it will definitely do logs of different bases, but most people probably don't have that kind of calculator. So this is a way that we can do it with the equal basis property in order to get the exact value. There's also a formula we'll talk about a little bit later that's called change of base formula. So that's another way you could change this, but this is actually going to be one where we can just use what we've already learned in order to get it. What we're going to do is we're going to start out by doing log base 464, and we're going to set that equal to x. So if we solve for x, we'll get the answer to this. Then we're going to change this from log form into exponential form because it's going to make it easier for us to solve. The base, to do that, you're going to take the base, raised to the power after the equal sign equals whatever you have left over. So I changed it from exponential form, I'm sorry, from log form to exponential is what I did. So base raised to number after the equal sign equals the 64. So now that's done. From here, we're going to use the equal basis property we just talked about in the last section. 64 can be written as a base of 4. That's going to be 4 to the power of 3. And so now I know that x is equal to 3. And the 3, in fact, will be the exact value for log base 4 of 64. So that's the final answer, x equals 3. So we're able to do all that without a calculator. By the way, one thing that I'll mention about these ones that we just did up here, log 5 and ln 7, it used to be that before calculators, used to actually have to carry around these big books of log tables. Now that's definitely before my time. I'm not that old, but my dad definitely had to use that. There were big tables, and you'd have to look this up on a table and figure out what this decimal is. So thank goodness now calculators have all that programmed in there. We don't need to worry about bringing these big books around, but that's how it used to be before. So now we don't need to worry about that because it's all in the calculator. Okay, this here, we could do this by just punching that in the calculator, but certainly it'll do that for us. But just to give us practice a little bit with changing between the two forms, I'm going to go ahead and solve this in a similar fashion to what we did before in the last problem. Okay, so what I'm going to do is change this to an x, put an x on the side, and I've already put it in the base 10. Remember, if there's no number after the log, that means it's automatically a base 10. And the bases are small numbers. They're written a little bit lower like this, like we see here. So we don't have that in the original problem. So I have 10 to the x is going to equal 1 over 10,000. We want to try and get these both to be the same base. So what we can do here is we can change the 10,000. That's the same thing as 10 to the 4th power. It's a 1 with 4 zeros afterwards, so 10 to the 4th. And then we can change that now to 10 to the x is equal to 10 to the negative 4. So now we have both the bases the same. We're going to set the exponents equal, and so we get x is equal to negative 4. Okay, and that would be the exact value. The same thing if you were to put this in your calculator, 1 over 10,000, hit the log button, you should get also negative 4. So 2 different ways we can do that. Okay, let's try another one. Okay, in fact, I'm going to try log of 0. So log of 0 I'm going to try, and let's also try log of negative 2. Okay, or actually we'll do an ln instead, ln of negative 2. if you try putting these into either one of these into your calculator, what's going to happen is you're going to get an error. Because, so if I put that in there, log, and put 0, it says undefined. In fact, this one is also going to say undefined. Okay, so now we're starting to get into some situations where not every number actually works inside of a log. 0 didn't work, -2 didn't work. So because of that, we have to take a look at what a domain of a log is. Domain would be the numbers that we're allowed to put into each of these. Okay, so for both of that, we're going to have to look at a graph. Okay, so what I did here was I drew in the graph. This is the original graph of, this is y equals b to the x. And this here is x equals b to the y. This is would be the inverse. Notice that with inverses, the x and the y are switched. So if I have 0, 1 on the original b to the x graph, then I have 1, 0 on the log graph right here. So I created this by just creating a mirror image. It's got to be reflective about the line y equal x. We talked about that in the inverses section. So if you take the red line, you flip it over the dotted line, you'll get the green line here, which is x equals b to the x. This is also y equals log base b of x. Okay, so actually I'm going to use that instead. So I'm going to erase this one because it's better for us to use the log. Okay, so this green line right here, that's a log. Okay, so that is our graph. Now from this graph, we actually have an identity. We have y equals log base of, if I put a 1 in there, or if I put so that's basically, that's the base here. So if I put in, sorry, not that, that's not what I meant. If I do, so I have this, because I have the point 1, 0, that means that log base b of 1 equals 0. That's actually a property I can get from the graph. If I put in this point 1, 0 here, because we see it crosses, I put a 1 in for x and a 0 for y, we're going to get this identity here, log base b of 1 equals 0. Also, if we were to change this, we get b to the 0 equals 1. So if we change the log form to exponential, we get b to the 0 equals 1. So that's actually where that property comes from. Why, if you take any number raised to the power of 0, you get a 1. It's actually because of this. It's because of the log graph that we have. That's the reason why we have that property in the first place. Okay, so it's a couple properties. We'll talk about log properties a little bit more in a later section, but I just wanted to talk about these two properties first. So if you have, doesn't matter what base it is, you can try it on your calculator. If you do ln of 1, you'll get a 0. If you do log of 1, you'll get a 0 on your calculator. That's a property how it works. Now, also what we're going off of on there, and here's some key points, by the way, we have on that log graph. We have 1, 0, and we also have the point b, 1, or actually it would be, I have to move that down. So right here, that would be b, 1 right there. So these are the two key points. And the reason why I mention these key points is because later on we're going to be graphing these. So we have to know what these two key points are. 1, 0, and whatever the base is, it's the base, and then 1 we have there. So the domain, let's look at the green line. Notice that for the log graphs, it's only going to the right-hand side, which means that you're only allowed to put positive numbers in for x. You can't use 0. And in fact, what happens here is there's a vertical asymptote at that point. So that's actually what this says down here. The domain of log base b of x is greater than 0. Okay, so it says the 0 is not included because there's the vertical asymptote that's there. So it'll just be x greater than 0 only. and it doesn't matter what the base actually is, you're going to have the same domain. So a couple questions they'll ask you in here is how to find the domain. All you're going to do is take whatever is inside the log and you're going to set it to be greater than 0. So that's what the base graph does. So for instance, this one here, ln is a log base e, so you're still going to do the same thing. If you want to find the domain, all you're doing is you're taking the whatever's inside and you're setting it to be greater than 0. And then we're solving. So x is greater than 7/2. And if you want to write it in interval notation, it would be 7/2. So 7/2 to infinity. Okay, that would be your domain. We have a parenthesis here. 7/2 is not included. Okay, so that would make the inside 0. We know we can't do ln is 0. We get an error. So that's why it's just greater than only. And that, it doesn't matter what the base is. Like this next one, we're going to do exactly the same thing. We're going to take whatever's inside the log and set it to be greater than 0. 6 minus x greater than 0. Now, if we move that over, we get -6. But what we'd have to do here is divide both sides by -1. Now, when we do that, remember that you have to flip the inequality sign. Whenever you take an inequality and you're dividing it by a negative number, if you're dividing by negative or multiplying by negative, that's going to flip the sign. So this problem, the answer is going to be -infinity to 6 because the sign got reversed there. So this is actually the only time where you might be able to put negative numbers into here and get an actual answer because there's a minus in front of the x. So if I put any negative number in for x, negative will turn into a positive and make that a positive number inside, which we are allowed to do. This one is a little bit harder. This one here, we're still going to set up the same. We're still going to do x plus 2 over 2 minus x. We're going to do greater than 0. Now remember, these kind of problems, you have to use either a number line or a table method in order to solve it. So first, I'm going to just take each of these and set them equal to 0. So I get -2, and I get x is equal to 2 here. So I get -2 and +2. Well, then what I can do is I can either use a number line method or table method. Let me just use I'll use the table method here in this case. We're going to put the two numbers that I have on here. I have -2 and 2. And this is the type of problem where I have to put in test points to see what they are. So let me put in -3. I'm going to put in a 0. That's between -2 and 2. And I'm going to put in a 3. I want to put these into the expressions on the left-hand side and just indicate whether I get a plus or minus. -3 plus 2 is a negative. 2 minus -3 is a positive. I put 0. 0 plus 2 is positive. 2 minus 0 is positive. 3 plus 2 is positive. 2 minus 3, negative. So I get, if I multiply these down, I get negative, positive, negative. So the only region where I ended up getting positives is between -2 and 2. So for this problem, so I guess, yes, I did put the table down below here, but I just wanted to draw it up there for you so you can see how it's set up. But on this case, the answer would be -2 to 2. Okay, so again, the 2 is not included on either end because we don't want it to actually equal 0. But any number between -2 and 2, anything we put inside here is going to work. Okay, so that's our answer, -2 to 2. You only have to do a table, by the way, if you have a fraction. So that's what told us to use a table in the first place. If you have some kind of rational expression here like that, with an x on top, x on the bottom, that's a case where you want to use this type of process. Okay, so now we're going to start getting into transformations on these. Okay, so transformations, we want to look at what the base graph is. And this is the graph of y equals log base 3 of x. The first key point we have here is 1, 0. Now the other one that we have is the base b, 1. So I have 3, 1 is the next one that I have. So again, whatever the base is, you just go to that x value. So I went to the x value of 3 and then it's 1. Okay, so those are the key points that this graph goes through, and this is the same key points I'm going to use to graph this. Now, to graph these, this is similar graphing tool than what you would have for the exponential ones. When you do these in MyOpenMath, what you'll do is there's a button that you'll see in there. So this is the tool, and you're going to see this with 2 dots. That's what the tool looks like when you do these in MyOpenMath. What you do first is it's another one that requires 3 clicks to get your answer. So if I wanted to graph this one, for instance, I would first click on the y-axis because that's my vertical asymptote. And then I would click on these 2 points and that would lock in your answer. So again, you always need 2 points. So that's why I'm labeling them here. And so that way we know what to do when we graph them in MyOpenMath. But let's do this one by hand. This one says -4. What that does, it's going to move everything over 4 places to the right. It always moves it opposite direction of what you see inside the parentheses. So if it's a minus, you actually move it in the positive direction instead. Okay, so I move that over, and I get this here. That means these 2 points are also going to move over. So this one I'm going to move it 4 places over to the right. That's going to be at 5. So I have a point that's going to go right there. This point moves over 4 places. It's going to end up being out here at 7. So I have to go 1 more. It's going to end up being about right there. And then the graph is going to look like this. So if I was graphing this in MyOpenMath, I'd click on the x value of 4 because that's where the vertical asymptote is. Then I just click on these 2 other points. That's how we do these graphs. There are no flips on this one, so that's why we just did it exactly the same as the original one. The next one, however, we have a negative sign that's in front, which means we have a flip. This is the graph of y equals log base 2 of x, because that's the base that we're given here. The points it goes through would be 1, 0, and it also goes through 2, 1. The base is 2, so we put that in as the x value, and that's 1. So that's going to be our 2 key points that we're going to use to draw our other one. We have a +3 this time. +3 means that we have to move the graph 3 places to the left, opposite direction of opposites of the sign here. Instead of +3, we move it -3 instead. Now, the negative out front, what that's going to do is it's actually going to flip the graph like this. So this blue dotted line, the graph will flip over, and that's what it's going to look like. That's what the graph is going to do here. It's going to actually come down instead. So that dot is still going to be on the x-axis, basically 1 away. So this point right here, we're just going to move that 3 places this way. So it's going to be at -1 right there. But this one actually gets flipped down to the bottom. And so we're going to have the other point's going to be right here. So it's going to go through and look something like this. Okay, so again, the graph flips over. The negative on the outside flips the graph over the x-axis. If the negative was on the inside, that would flip it over the y-axis. But out in front, it just flips it over the x-axis, and that's what the graph will look like. All right, so next one. Okay, so this here, we have an ln graph. So y equals ln. Now this is actually, let me write it this way. Let me write it as a log base e of x. That's what ln actually is. So log base e of x. Here's the key points it's going to go through. We have 1, 0. And then right here, this is e, comma 1. The letter E, this is about 2.7. So we have a point, it goes through 2.7, comma 1. That's the base of the log. And so that's what the point it goes through. So E, comma 1 is the other key point that you have. Now this question, you won't be using the graphing tool for something like this because the graphing tool only deals with whole numbers. So if it gives you one with an E, it'll likely be a multiple choice question because you can't use the tool for that. Now, before we jump into the graph, we first have to take a look at what the original one is, and we have to do a little modifying with that. Transformations work if the x comes first. So I'm first going to switch these two things, so that way the x comes first. So I have negative x plus 1 is what I get there. Well, then what I'm going to do is I need to factor out a negative, because I want to get x to be positive. The transformations only work if I have a positive x. So I'm going to factor out a negative, and that's going to flip this sign as well. So I get negative x, so I have inside the parentheses is x minus 1. If I were to multiply this out, I would get the same thing I started with, negative x plus 1, which is also the same as 1 minus x. So this is a problem where I have a negative inside. So negative inside means that I'm going to flip this graph and it's going to look like that. Okay, so the graph actually opens to the left because the negative inside. Negative inside flips it over the y-axis. Negative on the outside flips it over the x-axis. So negative on the inside means we flip it over the y-axis. All right, so now, and also what we have is we're gonna go based off of what's inside the parentheses, not the original one. Inside the parentheses, we have a minus 1, which means the graph is going to move one place to the right because there's a minus sign inside here. Okay, so minus, we move to the right. So then this graph, this dotted line, the whole thing shifts over 1 to the right, which means this dot that where it crosses here, we move that one place to the right. That tells us that the graph is actually going to go through the origin there. Now this point is another one that it goes through, this point right here. We're going to move that one place. So it's about negative 1.7. So it crosses about right there. And those will be our 2 points, and we'll just draw in the graph is going to look like this. Okay, so that's your final graph will look like. Again, these are going to be multiple choice, so just choose the correct shape based on that. All right, now this time we've got a log with no number underneath. So this one here, it doesn't show that extra key point, so I'm going to draw this in instead. The point out here that's going to be at 10, 1. We also have 1, 0. This is the graph of y equals log of x. Okay, so that's a log base 10. So if there's no number there, it's always a base 10. So in fact, this graph is actually going to extend all the way out, and it's going to cross through at 10, 1. We just didn't see it in the original one that was given there. So these are our 2 key points. Now I have a negative, I have x plus 2. That tells us that we have to move this 2 places over to the right, but I also have 2 negatives. So first let's do the 2. Instead of plus 2, we're going to move it to the left, opposite direction of the plus sign there. So left, we have to move, not right. Okay. Now we have to figure out what the graph is going to look like. So first, I have a negative sign that is on the outside. What that's going to do is the graph is going to flip and do this. So this would be y equals negative log x, would be that. The negative on the inside, that's going to flip that over to where now the graph is going to, so if I do this and flip it over the y-axis, the graph is now going to fall, and this would be negative log negative x. Okay, so putting a negative there will flip that over. So now your final answer should look something like this one here. So we're going to, again, what that'll look like, let me try and draw it in with the actual points here. The graph actually will still cross right here, and then the graph is going to kind of go like this, and then it's going to eventually cross over at -10 way out that direction. Okay. So that's what the graph is going to look like. So let me actually draw it down here instead, because this graph is not big enough to show that. Okay, so we have this dotted line at -2. We see that the graph is going to cross a distance of 1 away from the vertical asymptote. So it means this is going to cross right here at -3, 0. And then from that point, so from this one, originally we had from the 1, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So I go here 1, 2, 3, 4, 5, 7, 8, 9 here. And this is our -1. It's going to be right there. So the graph itself is going to come down and go through there and look like that. So the key points will be -3, 0, and then this one over here. So we went over another 9, so -12, -1 is where that other one goes through. So that's what the final graph is going to look like. Okay, so with the 10, that means that that's the special key points that you have there. It's the base, 1 is what you have. All right, now the last questions that are in this section that we'll take a look at are some ones where we have to solve by changing something into exponential form. Okay, so that's what these next ones are going to do that we'll talk about. All these ones here are ones where you have to change from log form into exponential form. Okay, that's what all these are going to do. So that's how we're going to solve these. We want to change all of them into exponential form and then solve them. So this we have log base 5 of x equals 3. To solve that, take the base of 5. We're going to raise it to the power of 3. And that's going to equal x. The base raised to the number after the equal sign equals whatever you have left over inside. So 5 to the 3rd equals x. 5 times 5 times 5 is 125. So that's our answer, 125. That's what we get for x. 5 times. So make sure you don't accidentally do this quickly and get 15 as the answer. It's 5 multiplied 3 times. That's why we get 125. Next one, we have x to the 3rd equals 1/8. The base raised to number after the equal sign equals 1/8. So x to the 3rd equals 1/8. Base raised to number after the equal sign equals whatever you have inside. We need to, in order to solve this, we need to take the cube root of both sides. So I'm going to do the cube root of x cubed is going to equal the cube root of 1/8. We don't have plus or minus here because you're taking the odd root. If you're taking an even root, you need plus or minus, but we're taking an odd root, so we only have one answer here. You're going to do the cube root of 1 and the cube root of 8, which means that you're going to get 1/2. The cube root of 1 is 1. The cube root of 8 is 2. So 1/2 is your answer there. Okay, next one is we've got So this one we want to change into exponential form also. 4 squared. So 4 squared is equal to x squared plus 9. The base, raised to number after the equal sign, equals whatever is inside the parentheses. 16 equals x squared plus 9. We want to subtract 9 from both sides. We get 7. Okay, now this is one where we're taking the square root of something, so that's an even root. It means we are going to get plus or minus this time. So we get plus or minus root 7 would be equal to x there. So square root both sides, and that's our two answers, plus or minus root 7. You only get plus or minus if it's an even root we have there. Okay, so a few more of these that we'll do. All right, so next we've got this one here is you take the base and you raise it to the power of, raise it to the number after the equal sign. 5 squared equals 4x plus 5. Base, raise the number after the equal sign, equals whatever you have inside there. That's how you do that. 25 is 4x plus 5 there. Subtract the 5 from both sides, you'll get a 20. If you divide both sides by 4, we get x is equal to 5. Okay, so 5 would be the answer on that one. So the key again is just change it to exponential form. If you just do that, then that's all you have to do, you're set. Okay, let's do the same thing on this one. Fractions, same thing, it works the same way. Okay, so we're going to do the base, raise the number after the equal sign, equals 3x minus 7. All right, so base raised to the power of 3 equals this. So it's always the same process on that. Now cube means we have to cube both of those. So we're going to get 1/8 there. All right, so now to clear that out, you probably want to multiply both sides by 8 in order to clear that. So let's do that one. Let's do that next. All right, so multiplying both sides by 8. So I have, just write that over here, 8. 8, and then I have 1/8 equals 8 times 3x minus 7. 8 on both sides. 8's cancel, we get a 1. If I'm multiplying 8, I'm multiplying this by both things here. So 24x minus 56. Going to add 56 to both sides, and I get 57 equals 24x. And I got to divide both sides to solve for x. So in this case, we get a fraction, which is okay. It's perfectly fine to have something like that. So if we divide both sides, we get 57/24 equals x. And that's what we'll get right there. Okay, so next one we have is one that has an e that's in it. Okay, so this one here. So for this, what we actually want to do, it's going to be easier for us. This is a case where we actually want to change it from exponential back into a log form. That's going to make that easier to solve because the variable we want to find is up there. Now, like I mentioned earlier, you can't just make this e to the 4th power. That only works if there's a 1 here where you can do that step that we did earlier. So instead, what we're going to do is we're going to change this back into log form instead. The way we do that is the e. So I have log base e that I have there. Okay, the exponent is going to go after the equal sign, and then we put the 4 here. I could also write that as x plus 5 equals ln 4. To solve for x, we just have to subtract the 5. So I get x is equal to -5 plus ln 4, if you want to switch the order around and make it a minus, that's okay as well. But this is fine as is here. So x is equal to -5 plus ln 4. All right, that's it. We'll just leave our answer like that. So in this case, we could get a decimal answer for it if it asks for it, but this is actually the exact answer. So it's better to go ahead and leave it in that form. Okay. So what I want to do next is I want to jump to 5.5. We're not going to finish this section, but I do want to go ahead and at least introduce it, at least these properties I want to talk about a little bit first before we get into more. So we'll finish the rest of this one up tomorrow, but we've got log properties here. So here's a list of all the different properties. So I'll leave that up there and I'll let you take a look at that for a little bit here so you can see. But there's 7 different properties. Now, these first two, first property there, property number 1, we already talked about that when we had the graphs. Okay, so the graphs that we had up there earlier, I told you that log base b of 1 equals 0. That's essentially, that's the x-intercept of a log graph, and it doesn't matter what the base is, they all go through that same point, 1, 0. And so this is the reason why where we get that point from. And as you see, it doesn't matter the base. We have a log base 3 of 1 is 0, ln of 1 is 0. So that's that one. Okay, so next we have log base b of b. So if you have the base, the number after, they're exactly the same, you get automatically a 1. So here's some examples of that. Log base 2 of 2 is 1. ln of e is equal to 1 because that would be a log base e of e. So whenever we have that, that's the same. And then log base 10 of 10 is equal to 1. If you're wondering why do we have this property, well, if we change this property into exponential, you would have b to the 1 equals b, and that is a true statement. So that's the reason why we have property number 2 that's there. Now these other ones are some additional properties where if we have a log as part of an exponent. So this is b raised to log base b of m is what that says there. The 2 b's, essentially that's going to cancel out. So what this is saying is if I have b raised to log base b, I'm just going to end up with the whatever part is after the log. So for instance, if I have 2 raised to the log base 2 of 5, that just simplifies to 5 only. 5 raised to log base 5 of pi, that's this pi. Whatever is after the log, that's what you get for that one. These next ones here, if you have log base b of b raised to the r, you get r for the answer. So if I have log base of 3 of 3 to the 7th, you're just going to get 7. If you have a 2 and a 2 here, then you just get the exponent left over on that part. Now the reason why that is kind of because of rule number 5 here. Rule number 5 says that if these are all different, you can take the r and move it down in front of the log that we see here. So we have something like this. Log base 3 of 5 to the 8. The 8 can be moved down in front, and these are both equal to each other. These are both exactly the same. If we were to put these both in the calculator, we would get exactly the same answer for those. Which is the reason why this part, number 4, turns into just r only, is if we use property number 5 and bring the r down in front, you would have r times log base b of b, and we know log base b of b is 1. So essentially you just have 1 times r, and that's the reason why you have r there. So 4 and 5 are kind of similar to each other. Then the last two, this is more algebraic in nature of why you want to do something like this, but we have a b here and you have the m times n. Okay, so if you have a multiplication inside, we can split it up into 2 different logs with a plus. And if it's division, it turns into a minus. So you can see the examples that we have here. We have 3 times 5. You can split it up into 2 different logs. Log base 2 of 3 plus log base 2 of 5. 24 over 6 is division. So then you have the top one minus the bottom one. Question that often comes up is, why would we want to expand all that out? Wouldn't that make it more complicated than what we had before? Well, as it happens, For those of you that are going on to calculus, these are actually some properties that you're going to be using to simplify expressions in calculus. Sometimes a calculus operation, it's hard to do if you've got a log with a bunch of things inside. So the calculus becomes easier if you can separate them into simple logs. And so that's actually the reason why we have properties 5, 6, and 7. That's primarily to make things easier for calculus operations later. So it may not make much sense to separate all this now, but it will make more sense for those of you that are going on to calculus. So that's why we're studying these properties, because ideally what you're doing here is you're simplifying algebraic expressions to make the calculus easier. That's essentially what you're doing with these. So with that, let's go ahead and continue, and we'll do a couple of these first. We'll do these numerical ones, and then all the algebra ones, we'll just do those tomorrow, next time. So first we'll start with this here, find the exact value using log properties. So what I would want to do first on a problem like this is I would want to change this into, or do log base 3, and I'm going to change this to a rational power. Okay, so that is so what I do there is it's the number inside the power, and the 3 is a 1. I just divide it by the 9, which is the index that I have on the root. So if I change it, it becomes 3 to the 1/9 power. So one of the properties that I'm going to use on that is I'm going to use up here, property number 4, says that if this number, the base, the number after it are the same, then my answer is just going to be the exponent. So I'm just going to put my rule number 4, so that way when you look back at this later, you'll know what rule that we actually use. So that's rule number 4, or property 4, technically is what it is, property number 4. That's what allows us to do that. Let's do another one. We have e to the ln 6. Now ln is the same thing as a log base e. So I have a situation where I have the base and this one are the same. Well, that's going to be a rule number 3. Property number 3 allows us to use that. So this and this, we just end up with m left over. So this equals 6 by property number 3. So this should be really property as well, but you get the idea here. So that from the list, there's property. Okay, so e to the log e, that essentially cancels out, and we just get 6. Okay, let's take a look at this one. So for this, we want to try and get the inside these brackets here. Let's work with that first. You want to get both of these to be the same base. So 1/2, and you want to make the 1/4 into a 1/2 as well, so we can use those properties. So here's what it's going to look like. We have log base 2, bracket, log base 1/2, and I'm going to change the 1/4. Now 1/4 is the same thing as 1 squared over 2 squared, and that's the same thing as 1/2 squared. So I'm going to write this as 1/2 squared inside there. So I changed the 1/4 into a 1/2 squared. The only reason why I'm doing that is because I can use property number 4 to change this here. So what's going to happen is inside the brackets, all this is going to turn into a 2. And property number 4 tells us we can do that. So 1/2 and 1/2, if you have that, that was just our whole problem by itself. You would just get the exponent, which is 2. Now I have log base 2 of 2, and that's equal to 1, and that's from property number, let me give you the property, that was property number 2, allows you to do that. So this right here, I'll just write that underneath, property number 2. And then this one here was property number 4. Okay, so 2 properties we use there. The first property we use to simplify the part inside the brackets. We got a 2. And then it turns into a 1 because of property number 2. So we use 2 different properties on that one. And here's the last one that we'll do for today. Okay, so this one is got a plus. We have a log base 5 of 6 plus log base 5 of 7. That's what that says up there in the exponent. So first, what I want to use here is I want to turn this into, I'm going to do this, and this was property number 6. Okay, so property 6 allows us to take the plus and turn it into a multiplication. So now we have that done. So of course that's equal to log base 5 of 42, 6 times 7. Now this part, we're going to use property number 3 in order to change this back into a, that's going to change into a 42. So again, what property was it? We'll go back to it again, property number 3 right here. B raised to log base B of m equals m. That's the one that we're using here. So that right there, we're going to use property number 3. Okay, so we use 2 properties on that one. Property number 6 to get it from plus to a multiplication. We simplified it. And then 5 to the log 5, we'll use property number 3 to change it into a 42. So that's all I want to do for today, because the next ones start getting into algebra. And so we'll continue that next time. And so for this week, we're basically just, your homework is covering all the way up through section 5.5. So 4.3, 4.4, 5.3, 5.4, and 5.5 are the sections for this week. So we'll be able to finish up all of 5.5. We will finish up tomorrow, and we'll probably start 5.6 as well. But this week you're only responsible up through just 5.5. So we'll go ahead and end it there. So does anybody have any questions at this point? Okay, it doesn't sound like anybody has any questions here, so I'll just go ahead and I'll end this meeting. As always, let me know if you have any questions. Enjoy the rest of your day. See you guys tomorrow.